Good afternoon and welcome, everyone. My name is Sarah Lamonaco, and I am the Alumni Relations Officer with the Faculty of Applied Science and Engineering, as well as the Program Lead for the Skule Lunch and Learn. I would like to thank all of you for kicking off the 2023-2024 Skule Lunch and Learn program with us today. It's so wonderful having you here. With alumni tuning in from all over the world, we have guests joining us from 4 different countries, including Canada, Ecuador, Hong Kong, and the United States. Before starting today's presentation, I wish to acknowledge the land in which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and we are so grateful to have this opportunity to work on this land. Now, I hope each and every one of you is excited about today's presentation, as our guest speaker is an esteemed figure in the field of biomedical engineering and access innovations. With a wealth of accomplishments in his field of expertise, our speaker has made significant advances to helping improve the quality of life of children and youth with disabilities through groundbreaking research and innovative inventions. Professor Tom Chau, his research is so perfect. It's the perfect example of how U of T's commitment through the Defy Gravity campaign aims to drive scientific discovery for tomorrow's game-changing ideas and breakthroughs, which ultimately help to completely change what's possible in our world. Now, a quick housekeeping item: at the end of today's presentation, you will have time for a formal Q&A session. Should you have any questions, please submit them using the Q&A button at the bottom of your screen. And for the individuals who submitted their questions during the registration period, thank you for pursuing your curiosities and sharing your insightful questions with us. Now, without further ado, I am pleased to introduce my trusted collaborator, the MC and Chair of the Skule Lunch Learn program, Lori Hevola. Lori is not only an Electrical Engineering 65 graduate, he also stands out as one of our most devoted and actively involved alumni community members here at U of T Engineering. For over a decade, Lori has served as the chair of the Skule Lunch and Learn program. He has consistently contributed his time and expertise to foster an atmosphere of innovation and knowledge sharing within our engineering community, all while remaining unwavering in his commitment to preserving the beloved traditions of our Skule Lunch and Learn program. And with that, please join me in welcoming Lori Hevola, who will now introduce our speaker for today's session.
Thank you, Sarah, for your very warm introduction. It is my pleasure to welcome our guest speaker today, Professor Tom Chau, who will introduce recent advances in non-invasive brain-computer interfaces and exemplify how some of these technologies are being applied clinically to expand participation opportunities for children and youth with disabilities. Tom, in addition to having master's and PhD degrees, has earned a number of honors: Order of Ontario, the Canadian Academy of Engineering Fellowship, Fellow of the American Institute of Medical and Biological Engineers. He is also a licensed engineer here in the province of Ontario and is a professor at the Institute of Biomedical Engineering and a distinguished senior scientist at Holland Bloorview Kids Rehab Hospital. He holds the Raymond G. Chang Foundation Chair in Access Innovations. His research focuses on the investigation of novel access pathways to facilitate communication for children and youth with severe physical impairments. He has published over 220 refereed articles, trained 100 graduate students, and held numerous patents, many of which have been licensed to industry. His lab has developed numerous access innovations that are being used by children and youth locally and abroad, including the virtual music instrument, a computer vision-based software tool that allows children of all abilities to play music, and a vocal fold vibration device that enables communication by humming. His lab has created a variety of brain-computer interfaces that facilitate communication and control through mental activities. These innovations help to establish the first pediatric BCI clinic in the world. His lab has been featured in national and international media. His contributions to science, engineering, and the quality of life of children and youth with disabilities have been recognized with numerous awards, too many to list here. And now, without further ado, please join me in welcoming our guest speaker, Professor Tom Chau.
Thank you, Laurie, for the very kind introduction. I believe I'm sharing the screen now. Yep. Okay, well, thank you, everyone. It's a real pleasure to join you over this lunch hour. And I hope I'll be able to give you some new insights into this whole area of non-invasive brain-computer interfaces for pediatric rehab. So I'd just like to start with just a quick word disclosures. These are some of the companies that we've received support from in the past. Over the years, we've been really fortunate to have their in-kind and cash support in some cases on joint grants. And I also would like to acknowledge the army of graduate students and postdoctoral fellows who have contributed to the work that I'm going to tell you a little bit about today. And I also have to give a nod to my current staff coming from many different disciplines. We have a number of engineers on staff, research coordinators, research managers, and postdoctoral fellows. And lastly, I'd like to acknowledge the families and children who have contributed to the work I'm going to tell you about today. Without their inspiration and without them sharing the stories and their passion, we would not be able to do the work that we've done over the years. So let me start by giving you a little bit of rationale as to why we even ventured into this whole area of brain-computer interfaces, but access technology more generally. And I'll define that term very briefly. But many years ago, a mother of a child who was nonverbal said these words to me. She told me that it is a crime to keep her child in the jail of a non-functioning body. She believed very strongly that her son understood everything that was going on, and he had his own opinions, he had his own preferences, he had his own wants, but just he had no way of expressing those inner intentions. And so she felt that he was being trapped inside his own body and felt that this was a human rights violation. And when we read further, we realized that in the Convention on the Rights of Persons with Disabilities, there are actually 3 articles that specifically mention communication as a fundamental human right. So next, I'm going to show you just a very brief video clip of one of the parents we've had a chance to work with over the years, and she articulates very beautifully her wish for her son.
If I can choose one thing for my son, if I would want him to walk or to speak or to eat, what would I choose? And I think without a doubt, I would say, I want him to be able to communicate. Without the communication, there's so much that's closed to him. So by giving him the ability to communicate, we're giving him the ability to have a say in what goes on with him and around him.
So a really powerful statement, just underscoring how important it is for her child, but really every child to be able to communicate. And with the one of the incredible consequences of not being able to communicate is a social isolation. And this next short clip is from a young boy. Well, I mean, he's a young adult now, but we started working with him when he was about 4 years old, and he had a very promising future, and he still does. And at the time, he was using a technology that we had developed in the lab to communicate. And this particular clip was when he had started high school, and he was asked a question by the interviewer why he likes computer activity so much and why he's really so absorbed in doing computer activities. And the answer was not one that anyone would have expected. So I'm just going to play this for you.
I tried to replace it with digital
So I was heartbroken when I heard his interview, but his explanation for why he's so immersed in computer activities at school is so that he can be distracted from the loneliness. And so this boy, he has cerebral palsy, and as you can see, he communicates with great difficulty, and unfamiliar communication partners really have a hard time understanding him. And he communicates very slowly, so people oftentimes don't have the patience to sit there and listen to what he wants to say. So one of the consequences of not being able to communicate is this social isolation. And so that's why we're so passionate about addressing this challenge through applied science and engineering. So you might wonder, we're in 2023, and in our pockets we have so much technology packed in, even in our phones. How can we have so many children who don't have, the ability to communicate? And these two clips just show you the breadth of, functional abilities, but also the manifestation of disabilities that makes it so challenging. On the one hand, you have individuals who have very little mobility, very little functional movements, and oftentimes, even unclear and inconsistent facial expressions. And then on the other hand, you have individuals who might have a lot of involuntary movements. And so traditional devices like, tablets and smartphones, computers, et cetera, become completely inaccessible to these individuals. And this is why it's been such an elusive challenge finding a communication pathway for many of these individuals. So let me now move on to the notion of access technologies. So access technologies really try to bridge this gap and provide an alternative means for individuals with disabilities to interact with their world, to communicate. So we start with a functional intent. So somebody has something they want to say, something they want to do, and then there's an access pathway. So you can think of this as a sensing mechanism that picks up some signal from the body that has encoded their functional intent. So this might be a movement, this might be a sound, this might be a biological signal. And then we do some signal processing, and then use that process signal to control a user interface. So that user interface could be a communication aid, can be an environmental control unit, so anything that, to operate devices in your home, a door opener, a call bell, anything connected to the internet, a mobility device, like a powered wheelchair, for example, or any sort of computing device. So that's really the general framework of access technologies that we've been working with for the last couple of decades. And, access technologies can be categorized in a number of different ways, but this is just one taxonomy, and is really broken down into whether the individual has residual extent movement or no functional movement. So if they retain movement, you can think of these as all kind of motor-based or movement-based technology. So some obvious ones here, include like eye gaze, for example, moving your eyes, hitting a switch with your hand, hitting a switch with your head, for example. But more and more so, we're seeing individuals that don't have that single motoric pathway. And so then we move into the whole area of access technologies that don't require functional movement. So you've got vocalization, so things like speech recognition or decoding of keywords, and particularly for those with dysarthric speech or that's very unclear and unintelligible. This kind of technology is very helpful. And then we have technologies that harness peripheral nervous system signals. So these are things like the electrical activity on your skin, the electrodermal activity that is very labile to different emotional states, cardiac signals, for example, respiratory signals. These are very hard to control, but they do, in some instances, encode communicative intent. But today we're going to focus on technologies that harness the central nervous system, and in particular the brain. So as I mentioned, there are more and more individuals that we've encountered who don't have a single motoric pathway. So assuming cognitive capacity, we have directly gone to the brain to harness the brain activity. And so that gives rise to the brain-computer interface. So just a quick word about what is a brain-computer interface. So essentially, it's a technology that senses activity in your brain that is tied to a functional intent. And we have machine learning algorithms that translate the sense signal into something meaningful that can be then used to control an external device. So I'm going to introduce to you 3 different modalities for brain-computer interfaces. And these are modalities that we've worked on in our lab. And I'll give you a little bit of just the basics behind the modality and then give you an example in each case. So I'll start with near-infrared spectroscopy. So this is an optical technique. So it uses light to interrogate the brain. But what's behind this technique is that when you have a thought, you have a functional intent in your brain, some neurons are going to fire. And as a result of those neurons firing, the local kind of metabolic demand in your brain is going to change. In other words, because those cells are firing, they're going to require oxygen. So what you're going to see then is a change in the local concentrations of oxy and deoxyhemoglobin. So, the neurons are going to consume oxygen. They're going to produce deoxygenated hemoglobin, and then new blood needs to flow in to bring in new oxygen. So this kind of influx of new blood produces what's called a hemodynamic response. And the graph on the right shows what a typical response might look like. And there's a bit of delay after the neurons fire. A couple of seconds later, you'll see this change in blood concentration of oxy and deoxyhemoglobin. So just a little bit more about the technique itself. There is an optical window between 700 and 900 nanometers where water does not absorb as much light as in other wavelengths. So this window allows us to interrogate 2 specific chromophores, so oxy and deoxyhemoglobin, whose spectra are shown by the green and red graphs. And that's exactly what we do. So we introduce light into the skull, and that light penetrates the skull and just touches the surface of the brain. So it just touches the cortical surface of the brain. And so by measuring the amount of light that comes back to us at the detector, we can infer the level of activity in that part of the brain. So you can imagine having lots of emitters and lots of detectors, then you have lots of channels where you can interrogate the brain in different spatial locations. And there's been 2 techniques of near-infrared spectroscopy that we've been mainly using. One is called continuous wave, the other one's called frequency domain. And so just very briefly, continuous wave is where the emitted light is provided at a constant intensity, and we measure the light that is reflected back. And that's going to be obviously at a lower intensity. Some of the light is going to be scattered, some of the light's going to be absorbed by the tissue, by the hair, etc. But by measuring the level of light that's returned, we can infer the level of brain activity. The other variation of this is what's called frequency domain near-infrared spectroscopy, where the light's actually modulated, for example, by a sinusoid. And what we measure then is not only the intensity of light that comes back, but also the phase difference, so the delay in the light returning. So with those 2 pieces of information, we can actually estimate the absolute concentration of the chromophores, whereas in the continuous wave, we cannot. So that's the basics behind the technology. I'll give you one example of a brain-computer interface that we've let me just pause this. Oops, sorry. Let me just pause this so I can explain to you what's happening here. So this is a brain-computer interface that is able to decode emotional state, so affective state. So in this particular experiment, we showed children pictures that had positive valence, so positive emotions, like happy pictures, and then they were accompanied by music that was also evocative of positive emotions. And then we showed pictures that had neutral emotion, so like no emotion, and then pictures that had negative emotion accompanied by sound as well. And what you'll see on the screen is that there's going to be a color bar, in green for a positive emotion, red for negative emotion. And over the course of a couple of sessions, in fact, in a single session, children learned to control this, and then they came back for 2 more sessions to test this. It was quite remarkable how quickly they learned this. So this is what you'll see in this video, is that there'll be a series of images, and then you'll see the person trying to control their brain response, and you'll see the feedback, the green and red feedback on the screen. So this is the neutral image, and this is a sad image. So the bar should glow red. Back to neutral image. So this is a happy image. The bar should go green. And back to neutral. So you get the idea there. So the color of the bar was controlled strictly by brain activity, right? So the computer is able to predict the person's emotional response based on these measurements. And this is just a graph just to show you the difference in responses when a person's experiencing a positive emotion versus a negative emotion. And there's a lot of lines here because they represent the measurement made at different parts of the brain. But the point is that there's differences between the green and red lines. So the red is negative and the green is positive emotional response. And these are visibly discernible. So you can actually see with your eye that over the course of time, so time is running along the horizontal axes, these red and green lines really differentiate from each other, which is why the machine is able to detect those different states. So next modality I'll tell you about is transcranial Doppler ultrasound. So this is using ultrasound to interrogate the brain. And so again, just start with some basics. So ultrasound can penetrate the skull in in certain areas where the skull is thinner. So the kind of window we use, the sonic window we use, is the temporal bone, which is like kind of your temples, because the bone is thinner there. And what that allows us to do is to introduce ultrasound that will reach what's called the circle of Willis. So this is a network of arteries that bring in the blood that perfuses most of the brain. And in particular, we're interested in the middle cerebral arteries. You've got a left one and you've got a right one. And using ultrasound, we can kind of detect which side of the brain is preferentially activated. So it's a very coarse measurement, but surprisingly, it's actually very useful in many circumstances. And so the measurement is based on the Doppler effect. So if you think about sending in a sound wave, and the sound wave is going to be reflected by the red blood cells that are flowing through the artery. And when the blood cells are actually moving, then the sound that you're going to hear or you're going to detect is going to appear to be at a different frequency. It'll appear at a higher frequency, right? Because it's being reflected by the red blood cells. And when the red blood cells are moving faster, you're going to hear the sound reflected back at a higher frequency, right? So the difference between the frequency of the emitted sound and the frequency of the detected sound is what's called a Doppler shift. And so by measuring the Doppler shift, we can estimate the velocity of the red blood cells flowing through the arteries. And this is useful because these are rigid arteries. So to change the amount of blood that is perfusing the brain, there's got to be a change in blood velocity. So by measuring the Doppler shift, we can infer the level of activity on the left side of the brain versus the right side of the brain. So that's basically how the transcranial Doppler BCI, brain-computer interface, works. So I'm going to give you an example here of an online speller that we created a number of years ago. And to activate one side of your brain versus the other side of your brain, there are well-known activities that will do that for you. So, for example, what's called a categorical fluency or verbal fluency task, where you think of words that start with a certain letter. So, for example, you're told to think of words that start with the letter M. You might think machine, man, magic, mom, those things shown on the screen. The left side of your brain for most people will be preferentially activated. As opposed to when you imagine an object, a 3D object. So you imagine drawing the outline of a 3D object, or imagine, your hand moving through space. Well, it would have to be one particular hand, but let's stick with the object. So if you're imagining tracing an object in 3D space, the right side of your brain will be preferentially activated. And then you can also use hand imagery, but that will cause contralateral activation. So right hand, imagining the movement of your right hand will activate the left side of your brain, and vice versa. And this is just an example of the velocity signal that we can detect from transcranial Doppler ultrasound. And it's very subtle, but you can see that when the person is doing the word generation task, this is when they're thinking of words to start with a certain letter. There's a difference between the left and right velocities, right? The left velocity, as expected, is higher because this is a left lateralized task. So these very subtle differences a machine can be taught to detect these automatically. So these are two videos of ultrasound BCI spellers that we created. And the girl on the right, she's spelling hello. And I don't remember what the gentleman on the left is spelling. But it's a very slow modality. So it's like near-infrared spectroscopy, it's detecting a hemodynamic response. So it's a blood flow response. So it's very, very slow. But surprisingly, it's very accurate and requires very little training. So in the studies that we published on this, individuals were able to use this, on the very first time they were sitting in front of the computer. And what the person's wearing, you can't really see, but there's two probes that basically are attached to the side of the head. So that's the second modality. And then I'll close off with a couple of examples of EEG BCI. So for those of you who have heard of non-invasive brain-computer interfaces, probably the modality you've heard of is EEG, or electroencephalography, which is the most popular modality for interrogating the brain non-invasively. So the basics behind this is the so-called signal that you're measuring, the EEG signal you're measuring at the scalp. So this is kind of a cross-section of a person's head, and you have the skull and the scalp and the skull, and then the meninges and the different tissue layers, and the electrode sitting on top. And deep down inside, you've got the so-called sources, right? So these are the neurons that are firing. And when the neurons are firing, there's going to be an induced kind of extracellular current. And that's actually what's picked up by the EEG. But the thing is that you're not picking up the current of a single neuron, right? You're not picking up the potential difference from a single, due to a single neuron. It's actually many thousands of neurons that are generating a signal. So there's a blurring, there's a smearing of this information that's picked up at the electrode. And this is another view. So the sources are deep in the brain. The electrode is far away. So this is kind of what we call far field recording. And because the signal has to pass through so many layers of tissue, it is essentially what's called volume conduction. So there's all kinds of distortion, there's all kinds of attenuation. And, the conductive properties of the tissue will change the signal. The conductive properties of the electrode will change the signal. The orientation of the electrode as relative to the source will also affect the signal. So there's all these kind of confounding effects. So some people have compared the measurement of EEG to measuring the sound of a crowd cheering at a football stadium. You're not going to be able to make out the specific voice of one particular individual. It's more like the collective, the population sound that you're collecting, right? So in this case, it's the electric signal due to a whole population of electrons firing. And the other kind of limiting factor of this measurement is that the dissipation of the signal, the propagation of the signal is actually happening in 3 dimensions, but our measurement is really just a 2-dimensional projection. So technically, it's not possible for us to reconstruct the sources, location of the sources, but there are some mathematical tools that allow us to approximate. So let me give you an example of an active BCI. So an active BCI is one where you are consciously generating a mental activity. So, for example, doing math in your head, or thinking about thinking about words from a certain category, to start with a certain letter, or thinking about objects from a certain category. So the one example I'll give you here is one of visual spatial imagery, and I show this graph just to show you that there is actually a visibly discernible difference when we do this kind of task. So visual spatial imagery is basically imagining a very detailed image in your face. In your head. So, for example, you imagine the face of someone you love, and you imagine all the details in their face, their eyes, the wrinkles, and their mouth, their lips, and imagining all those details. Another spatial task might be to imagine an object rotating in space, or something flashing in space. So these are all different types of visual spatial imagery tasks. And what's exciting is that we can elicit activity in the back of the brain, in the visual cortex, when you do this kind of imagination. And this graph is a spectrogram, so it's a time. It's frequency versus time. So this is the frequency of the EEG signal over time. And in this band, so-called alpha band, we see a differentiation of activity when a person is resting versus when they're doing imagination, right? So there's a suppression on one side of the brain and an increase on the other side of the brain that is detectable by machine. And this is a graph showing the same idea. So this is an example of a active BCI based on visual spatial imagery. So in this case, what the person is imagining is an arrow flashing in one of 4 quadrants. And when they make that imagination, we actually see activity in the occipital cortex, so the visual area of your brain, the visual cortex of your brain, in the opposite quadrant. So when you imagine arrow flashing in the top left quadrant, we're actually going to see activity in the bottom right quadrant of your visual cortex. So this allows us to decode the direction that the person's imagining. And so what this person is doing in this task is that he's moving this pig icon through this maze. And he's telling the pig, which direction to go by imagining the arrow in the direction he wants the pig to go. And this is in real time, so it's actually the response of the system is actually quite reasonable, quite functional. This is just another example of using the same modality and same task, so visual spatial imagery, to move a robot. So this is the BB-8 robot from Star Wars. So this is a graduate student preference. So, but he's able to move the robot in different directions based on the arrow that he's imagining. Another example of an active BCI is very popular, is called a motor imagery BCI. So in this case, you imagine movement on one side of your body versus the other side. So if I imagine clenching my right hand into a fist, then I'm going to get measurable activity preferentially on the left side of my brain. And then if I imagine closing my left hand into a fist, I'll get activity that'll be higher on the right side of their brain. So it's a little bit more complicated than that. There's desynchronization and synchronization and variations thereof, and it depends on the developmental age of the individual as well. But that's the basic idea. And so in this video, we actually had children control a monkey on the screen. Sorry here. And the monkey's arms will rise to select a token or whatever reward that's presented on screen. And the child doesn't actually move. He or she just imagines moving the hand on the side that the reward shows up. And so we built like a whole kind of game narrative. So there's different scenes to allow these children to practice. So this is a really well-established brain-computer interface in the adult literature. And we've just started to explore this with children, and there are some limitations. But we can talk about those later. So another type of brain-computer interface is called a reactive BCI. So reactive BCI is one where you don't actually have to think of a mental activity. You simply react to the stimulus that's shown to you. So this is an example where you're shown lights, for example, and then there's accompanying sound. You're going to have a reaction to those stimuli. And it's that reaction that we detect. So here's an example of how we can exploit this kind of naturally occurring response in your brain. So what you're going to see here is what's called a P300 brain-computer interface. So a P300 is what's called an evoked potential that shows up in your brain. And this is often called a surprise response because it shows up when you see a stimuli that you don't anticipate. So one way we can exploit this, as you'll see in this video, is by flashing stimuli that's on the screen, because you don't know when the specific stimuli that you want to select or the target you want to select is going to flash. You're going to be surprised when it does. And when you feel surprised, we're going to see the brain response. So we'll know which target you're actually fixating on. So this is an environmental control. So the person is controlling 6 different things. Turning on a fan, turning on music, which you just did, controlling the volume of the music up and down, and then turning on and off a light. So all he has to do is look at the icon corresponding to what he wants to do. So if he looked at the icon for volume down, now he's going to look at the icon for volume up. He actually doesn't have to change his gaze. Now he's going to turn on the fan. And again, this is happening in real time. So you just turn on the light. As you can see, the response is quite quick. You just turned off the light. So this is entirely by brain control, right? There's no movement. There's no gaze detection or anything like that. So this is one last example of a P300 BCI or so-called reactive BCI. So this is more of a functional application. So it's a spelling application. So in this case, you're shown letters on the screen and the rows and columns are flashing at random or pseudo-random. So you don't know when they're going to flash. So all you have to do is look at the letter you want to type. And when that letter flashes, we're going to see the surprise of response in the brain. And so then we can tell the computer that this is the letter you want to type. Now, what's really cool about this particular speller that we created is that we also detect a second type of potential called the error-related potential. So that's a potential that shows up when you observe an error, when you notice there's something that was selected incorrectly, right? So for example, if you wanted to select the letter T and the computer typed the letter S, we would see an error potential in your brain. So we can tell the computer, you actually made the wrong guess, and the computer can go back to correct its guess or make a second guess. So in this video, the person is going to try to type the word listed, L-I-S-T-E-D, and the computer is actually going to make a wrong guess at one point, and we're going to detect the error potential, and then the computer is actually going to autocorrect and make a second guess, which almost always will be the correct one, correct letter. So just type the letter L. And now the person's looking at the letter I. So the computer correctly detected the letter I. Now they want to type the letter S. So the computer incorrectly detected didn't detect the letter S. Now that was very subtle, but the computer detected the letter T, and the person saw that that was not correct. And then the computer made a second guess and corrected the letter. So it's like auto correction on your word processor, but this is for brain typing. And this is just an example of the error potential that we actually see. So the dark line here is the error potential. So when a person sees an error, and this is the lighter line is when the correct letter is typed. So there is still a bit of a surprise of response, but what's interesting is that the error actually precedes the correct response. So it's almost like we're very vigilant and we're looking out for the error. And when we see it, we have an immediate response, and it's a much larger response than when the actual correct letter is typed. So we can then tell the computer to make the corresponding adjustments. So those are the three modalities of BCI that we've been working on, and there are many, many different other task paradigms and examples. But I thought I would just close by showing you a little bit about how some of this technology is already being translated into the clinic. So this is just an example of one of the little girls that's in our clinic, and her parents are there, and the occupational therapist is there to put on the headset. And in the clinic, children are able to do a whole bunch of different activities. So we use a non-invasive headset. As you can see, it's a commercial headset. It doesn't require any gel. It's a saline-based headset. So the electrodes contact the skull through a piece of foam that's dipped in saline solution, and that provides the necessary conductivity. So children are able to control video games, they control music on YouTube, they can control electronic toys. Over the summer, we had children in the summer camp watering a hose. So right here, she's doing a painting. So it's a motorized ball that we dip in paint, and then she can move the ball around. They can control electronic toys like driving this car. And then soon we're introducing powered mobility. So children will be able to learn to drive a mobile, a powered platform using their brain activity. And then music making is coming soon. We have an app that we're developing, and in communication. And then there's also a coding program that will allow children to learn to code using their brain. Oops. Okay. So we've had about 100 clients, 100 children and families come through the clinic so far. The clinic's only about 4 years old, and these numbers in the bar graph don't add up because they haven't been updated. But just to give you a sense that we have children with a wide spectrum of conditions, genetic conditions, cerebral palsy, brain tumors, motor vehicle accidents, and other conditions. So many, many different types of children are able to use this. And I'll show you this video. I just closed with this video from a recent media coverage of our clinic.
66 people have come through the program, including 15-year-old Zen, who lives with cerebral palsy. When he thinks of driving, the remote control car races around the track.
Now I see his personality coming out with this. So that's the most beautiful thing for me. Like to see him control that car, it's a physical thing. And the hope is one day that he'll be able to, control his own chair.
The technology is slowly being shared to treatment centers across Ontario, helping more families form a strong emotional connection.
There's a lot about him that I did not know until I started exploring what he feels and how he thinks.
And giving children a greater sense of independence. Rahim Ladani, CTV News. 66 people have come.
Oops, sorry. So his mom actually said later on in an interview that the moment she knew that he was actually controlling this, and he actually had a preference, was when she wanted to play a particular song, and he was, connected with the BCI to the computer, and he kept turning off the sound, the song, and she didn't understand why. And then she put on a different song, and then he played it. So he, as any teenager, he had a very strong music preference, and very specific music preference. He didn't like the song his mom was playing, so he kept turning it off. So that was for her an experience. really being seeing her son's personal preference and intentions being manifested. So as I mentioned, we have many different other functional applications that are being introduced with brain-computer interfaces, and the list just goes on and on. We're really just at the tip of iceberg in terms of the rehabilitative potential of brain-computer interfaces. So I just want to acknowledge the various funding sources that have supported our work over the years at our provincial government, federal government, number of private agencies, and private foundations as well. And I just wanted to, my very last slide here is to invite you to dream with us. In our lab, we have a hope and a vision that one day in the not too distant future, all children with all abilities will be able to fully exercise their right of communication. And I keep a log of what I call first word stories. And these are stories of children who have been able to communicate for the very first time in their life through technology. And one of my favorite ones is what's shown up on screen here, is a young man who we taught to use his mouth to operate the computer. And this was using a different technology at the time, not brain-computer interfaces. But after 2 years of training, he was able to use his mouth using, this was using thermal imaging to type on the computer. And this was the first word that he typed. He typed M-U-T-H, and all of us thought, oh, he's typing with his mouth. You know, he really gets it. But he wasn't finished. And he typed E-R. He typed mother. He called out to his mom. That was his very first word at age 25. And, you know, his mom waited a quarter century for him to call out to her. So these kind of first word stories are what keep us going, keeps us inspired. You know, research is challenging, you know, getting funding for the work is challenging, and a lot of disappointments, but, you know, it's these first word stories that really power us and keep us going. So thank you very much for your attention. I hope this has given you a sense of the possibilities of brain-computer interfaces for realizing the full potential of children with disabilities. Thank you very much.
Thank you, obviously, to all of the participants from the questions from our online audience, as well as in advance. Before we close, I want to thank Professor Tom Chau for being with us today. Thank you for being such an informative and inspiring presenter on the power of non-invasive brain-computer interfaces in pediatric rehabilitation. To everyone who joined us here today, we invite you to share your feedback on the Skule Lunch and Learn series. A link to the online survey is available in the chat function at the bottom of your screen and will be shared with all of you after this event by means of email. A link to the presentation will also be shared with all registered guests early next week because it was recorded today. Skule Lunch and Learn events are traditionally hosted on the second Wednesday of each month. Our next event will feature Professor Alison McGuigan on Wednesday, November 8th. She will discuss the use of artificial tissues in personalized medicine and drug development. In closing, I would like to thank you all for having joined us today for our presentation. With this, I hereby adjourn our first Skule Lunch and Learn event for the 23-24 program year. Thank you and have a good week.